Today we're going to go over a problem which is number 1 from worksheet 6 in the Academic Excellence Workshop worksheets. So basically what's happening in this problem is we've got a sphere and we've got a cylinder, and they're both rolling towards a hill with the same center of mass, linear speed, going horizontally, not like an omega or anything. And we want to know which one's going to roll higher up the hill. And so I've drawn a little picture, and we don't actually know this h. I drew it just of a general object rolling towards a hill, and that's going to be our idea of how high it goes. And so it turns out these cylinders and the cylinder and the sphere have some masses and some radii and stuff like that, but they turn out not to matter, so I'm not even going to tell you what the values are. But what is important is that the initial velocities are the same in each case. So here's what we're going to do. We're going to assume that the moment of inertia of some object, we're not going to start yet with looking at a sphere specifically or a cylinder. We're going to look at some object that has a moment of inertia of the form I equals b mr squared, where b is just some number. So we know that a sphere and a cylinder both complete this qualification because for a sphere, this b is just 2/5, and for a cylinder, it's just 1/2. Okay, so this looks a lot like a work energy problem to me because we've got some heights and we've got some rolling and we've got all kinds of energy that we can deal with and all kinds of work that is really well defined in this problem. So quickly, to find out what the work is, I first choose a system, and I say the system is the rolling object. And so we are going to in fact have work done, and that work's going to be done by gravity. So to find that, I said upwards is positive, and I made my lower bound 0 and my upper bound h. And notice h is bigger than 0, and that's because this way is positive. And then I said, well, gravity is negative if that way is positive, and I took this integral, and I got that the work is minus mgh. Now, just for a quick sanity check, we want the work to be negative, right? So this is a good thing. And we want it to be negative because the displacement is this way, and the force is downwards. And so our dot product is going to turn out to be negative in this case. Okay, so with that in mind, we just come over here and we say, what are the changes in energy of this system? Well, we know translational kinetic energy changes as well as rotational kinetic energy because the ball speeds up and it starts rolling faster. And so I can't really think of any others with this system, so we'll just leave it at that. So we already found just a minute ago that work is minus mgh, or we don't know h yet, but that's fine. Well, delta k translational, I know v final is 0, so final kinetic energy is 0, but I know initial, so I have to say, I'll go ahead and write it for completeness, 1/2 mv final squared, which goes to 0, minus 1/2 mv initial squared. I'm still just putting in a general mass. I don't know what this mass is, but I know it's the same for any given object. And then that's going to be plus 1/2 I omega final squared, which also goes to 0 because the ball stopped at that point, minus 1/2 I omega initial squared. Okay, so at this point, I can apply the rolling condition and also make some simplifications. I can say, all right, I is just b mr squared, and since it's rolling, omega initial is just v initial over r. Hopefully you can see this squared. Okay, well, one thing I noticed is that there's a mass in every term, so I'm going to get rid of those. And I also noticed that this r squared over here cancels with that r squared over there. And so what this simplifies to is minus gh equals 1/2 vi squared minus 1/2 b vi squared. Hang on, I realize what the problem is now. Okay, sorry, just a few minutes ago, I didn't copy down this negative sign. So now, I'm going to go ahead and also make all of these positive, because I noticed there are a bunch of negatives. And I'm going to say, dividing by g and factoring out some stuff, I'm going to say h equals v initial squared, and I'm going to factor out the 1/2 over here. And now I've got v initial squared, 1 plus b, and I'm going to divide that whole thing by g, which I moved from that side. And so now we see, all right, the h value for any rolling object that takes this form, rolling up a hill, is equal to vi squared, which we know is the same in both cases, and then it increases as b gets bigger. So for the bigger b, I'm going to get the bigger h, and we're going to find out that the cylinder is in fact going to make it up farther. So a quick intuitive way to think about that is to think, well, if they're moving with the same speed, it's harder to get a cylinder rolling. So it turns out that the cylinder had higher energy at the bottom of the hill. So if it just uses it up with the same work, it should probably make it higher up the hill. So that's it. This is our answer.